Hello students, welcome back. And from today onward is starting a new chapter, that's current electricity. Actually I was supposed to teach you optics first, but I have changed my mind because if we learn optics in contact classroom, that will be much better. So I have decided to start what? Current electricity, okay? Yes. So before this topic we have electrostatic also. I am not teaching that first because these two are little different ways. So I am starting with what? Current electricity. Okay, so listen, two things we have: electrostatics and electrodynamics. Electrostatic means your charges will be at rest and you're learning some property like what's the force, what's the electric field, potential, energy, flux. These 5-6 things we learn when charge is placed at rest. All these things we learn in what? Electrostatic. Then electrodynamics or current electricity call, here charges will be moving, okay, and you know that when charges are moving they will produce what? Current, okay. When charges are stationary, that we learn electrostatic, that chapter, they will produce what? Electric field, electric force, potential energy, flux, and these things they will produce, correct. When charge started moving, it will produce what? Simply current, okay. So we are learning current electricity means here charge will be in motion, okay. What's the meaning of current electricity? So okay, I already wrote here heading like current, electric current, okay. So how electric current produce? Obviously say when charges, okay, are in motion, when they start moving they will produce what? Electric current, right? Yes, they will produce what? Electric current. I am writing short, you write properly, okay. When charges are set in motion, they will produce what? Electric current, okay. Yes, when charges are moving they will produce current, and when charge is stationary is called electrostatic. And we are learning what properties? I said I will teach you after this, I think. So 5 properties mainly we will learn when charge is placed at rest. So one is called electric force between charges, electric field due to charges, then electric potential energy, and flux. These are the main thing we learn. Apart from this, we will learn capacitance also we learn, okay. So total 6 things we learn when charge is placed at rest. And when charge is moving, like this chapter, we learn what is a current and some instrument and working of this instrument. All these things we will be learning in this chapter. So here charges will be moving, they are in motion, so electric current will be produced. So when charges are in motion, they will produce is what? Electric current, right? Okay. Then you have seen that generally, like recently I learned our semiconductor, right? Their charge, when we say we have 2 type of charge, that's your holes means positive charges and electrons are negative charges, right? So look here, how charge moves. Generally what happens, if you talk about like positive charge, okay, just like hole we have learned recently, right now, these moves from, how they moves from high potential to what? Low potential. How positive charges moves? They moves from higher potential to what? Lower potential. Suppose you are talking a battery, then battery means positive terminal is called high potential, negative terminal is called what? Low potential. I can draw here a small picture. Suppose this is a piece of wire, you have some wire, okay. This is the area of cross section, and this you connected to some battery like this, okay. Yeah, negative terminal, positive terminal, okay. So if you have electrons and holes here, means positive charges, right? How they will move? Because understand one thing, this electron and whole things mainly we talk when you talk about semiconductor, okay. When you talking like here this chapter, generally we will talk about electron only, okay, because holes are very few in what? Conductors, okay. Here we will talk mainly about conductors, okay. So electron word mainly we use. Still, suppose you have positive charge, okay, this is positive charge, then what is the direction of positive charge? It moves from high potential to what? Low potential. In case of battery, positive terminal is called high potential and this is called what? Low potential, right? So they will move from what? This terminal, means this is the direction of flow of what? Your positive charges. And but if you have electron, means negative charges, okay, let me represent by a minus sign, then they will move in opposite direction like that way. Then, okay, positive charge I wrote. Suppose you want to write negative charge, means like electron, how they moves? They move from low potential to what? High potential, okay. That's done. Now we know that what is the direction of current. We call it conventional current, okay, general current. What is the direction of current? That we can tell by the direction of motion of these charged particles, okay. Yes. So direction of current we are talking, okay. Direction of current. How you represent direction of current? So either you can say like this one, same as direction of what? Positive charges. What is direction of the current? Conventional current we call it. Let me write here. Conventional current, okay. How the current flows in a outer circuit in a wire if you have is same as the direction of what? Positive charge. Like in this case, positive are moving from left to right, so that's your current. So in this case, in this circuit, current is flowing like in this direction, I. Correct. That's the direction of your current. So same as direction of what? Positive charges, or what? Opposite of this. Opposite to direction of what? Negative charges. Right now. Right. Okay. Holes like positive charge are moving this direction, so direction of current in outer circuit is also what? Same direction, right? Negative charge are moving that direction, so it's opposite to direction of what? Negative charge, right? Okay, so hope you understood the direction of current concept. Now, how mathematically you define current, okay? In maths, how you define, how you write as a formula. So, mathematical definition how you write in maths, okay? Mathematically how you write, watch it carefully. Current is what? Current is simply, you say that charge are moving, so we say the rate of flow of charge, okay, rate of flow of charge, that's what your current, okay, rate of flow of charges, right now. This rate of flow of charge, this is called what? Your current. So you can say two way, like how you say, one you can say word like average current, okay, average current. So let's say I average is what? How much total charge is flowing for the given time? So you write total charge flowing through some wire dq, that's total charge by what? Some time del t, right now. This is called what? Your average current, right? Yes. Or you want to write instant current. Generally instant current questions we will see. Instant current means a small current for the small time interval. So how you write instant current? I is equal to what? Simply rate of flow of charge. In differential format we are writing this, watch carefully, okay. Yes, total charge flowing by total time is what? Your average. Instant, both are same thing only, should not confuse, okay. So this is simply what? Rate of flow of charge, dq by dt, the differential format, so you can find what? Instant current. So here they ask questions to you. How they ask? Watch carefully, okay. In simple language, like in scalar form you want, right? The current is always scalar only, you can simply you can write, okay, or simply how I want to write, your current is nothing but what? Q by T, that's all. You can write this way also, okay. Yes. So if any equation is given differential format, you can use this equation, or direct values are given that this much number of charge are flowing in this much time, you can write this formula also, okay. Yes. Okay, instant current and average current you discussed, general formula is there. Now watch carefully. What will happen here? Either the rate of flow of charge equation will be given to you, you can differentiate and find the current, or sometime the rate of flow of current equation will be given to you, they will ask you how much charge is passing, so you can do integration, means if you want to find charge, then you write I into what? Dt, and integration on what? Both side. So this format also you can write from given time t1 to what? T2. Yes, you can do like this way also, okay. Also you know that this current is what type of quantity? Always a scalar quantity, right? Not vector, is a scalar quantity, okay. Yes, actually in real it's not even scalar, it's called tangent, but that's not in our syllabus. Our syllabus we have vector and scalar only, so we will call that scalar only, okay. But again it's confusing, because when we go to magnetic chapter, their current we will call again vector. It depends upon like whether somewhere we need direction, somewhere we don't need direction. So in this chapter, okay, we will call it what? Scalar only, okay. Okay. Okay, current is scalar, and unit dimensions, everything you know. Unit is what? SI unit is what? Ampere, you know it, okay. SI unit, right? Ampere we write. Okay, dimension also you can write, there is no problem. Dimension, right? M power 0, L power 0, T power 0, and A power what? 1. So dimension of the current we represent by ampere, simple. So A power what? 1. Okay. Okay. So here what I did, I have discussed the basic introduction of this, what is current. Okay. So once more, when charges are moving, they will produce what? Electric current. Okay. Yes. So positive charge, how they move? They move from the high potential to low potential. Right now, in case of battery, high potential means positive terminal, low potential means what? Negative terminal. So they are moving from here to here, positive charges. And negative charge move from what? Opposite of this, low potential to high potential. How you tell the direction of current? Direction of current, or also called conventional current, is same as direction of positive charge flow, right now, or opposite direction of what? Negative charge flow. Then how you define in mathematics that current is nothing but what? Simply rate of flow of the charge is called what? Your current. Correct? Yes. Okay, then you can say instant current and what? Average current. Average means little big current, so large means big charge by some big time, and instant means at particular point you are asking, so just differentiate. Okay. Yes, instant time. Okay, you can find charge flowing also by integrating on what? Both side, right? Okay, simply we can simply say current is nothing but what? Charge by time, right? Okay, unit and dimension all you have understood. Okay, let's move on. So right now we are interested in calculating that the full formula of what? Current. What's electric current through a wire? Okay. Okay, we have to see two situations. Suppose you have wire, then when you connect a battery with this wire, then what happening, and without battery what happening, that you want to see. Okay, so 2 points I am writing here. Okay, so first point I am writing like how I should say behavior of charges when no external field, or you can say potential also, is applied. What's the meaning of this? I wrote here something. We are interested in knowing that how electrons and how these charges are behaving in a wire when no field is applied, means no battery is connected to what? That wire. Just wire alone we have, means like this way. You have this wire. Okay. Okay, this is a wire of some cross section area A. Okay. Yes, and some length L. Correct. It has large number of electrons, right? Yes, free, because we are talking conductors here, they already have large number of what? Free electrons. Okay, so what we have just a wire. It's just a wire. Okay, yes, and it has large number of free electron. You know, like a conductor, the density of free electron is very high, like 10 power 28 per meter cube. Okay, it's very high. So there are large number of electrons are inside this conductor. Okay, and when no field is applied or no potential is applied, okay, how they are moving? They are moving randomly. Okay, few words I will talk here. Let's see one by one. Okay, so first, when no field applied, large number of electrons, free electron. Okay, right, free electrons are there, and what they are doing? They are randomly moving. Correct, na? Okay, they are randomly moving. Why they are randomly moving? Actually, listen carefully. Because large number of people are there in what? Large number of electrons are there in just 1 meter cube of wire. So what happens? They are moving because of what? Thermal. They have what? Thermal speed. Okay, let me write these words also. So first word we talk is what? Thermal speed and velocity. Thermal speed and velocity. Okay, this is the first word. So we know that they have some temperature. Okay, yes, initial temperature. So they have these electrons as what? Thermal speed. So they are moving, and this electron, if you talk an isolated electron, like one electron at what speed is moving? It moves around 10 power 5. Because remember this formula already we discussed, that RMS speed of these electrons. Okay, at what speed they moves? RMS, let's call something. Already learned. Remember this formula, 3 kT by what? M, right? Or 3 RT by M also you can write. In thermal physics we have learned this formula. Yes, so at this speed these people are moving, which is around 10 power what? 5 meter per second. Electrons, all electrons are moving and moving at what? Very high speed. But how they are moving? Randomly. What happens? There is very less space. So electrons start moving. Then what will happen? It will collide with what? Next electron or positive ions or the boundary of the your wire, right now. So what happens? Their direction get changed frequently. They are moving very fast, but how they are moving? Randomly. Suppose I show with the example of one electron. Suppose this is one electron, it started motion from here, it went here, it hit the wall, right, like this one. That direction change, it will come this direction, it hit another electron here, again its direction get changed, it can go somewhere here, then it goes here, right. So what happens? The direction changing frequently, again it can come like that way, okay. So what I'm saying, these electrons are moving randomly. They are moving. They have very high speed. How much? Around 10 power what? 5 meter per second. Okay. This is called thermal speed right now, or RMS speed of these electrons. But because they are moving randomly, so overall the displacement of this electron is what? Almost zero. Yes. It's just like what? Suppose you have a drunken man and close him in a room, right? Yes. There's a man and you have closed in a room, then what will happen? He will move, hit this wall, that goes to other wall, hit that wall. So keep moving. He is moving at good speed, but overall displacement of that person inside a closed room is what? Zero only. Exactly same thing is happening to what? Electron. Electrons are just drunk people. They are randomly moving, okay. They're moving at very high speed. Look here, 10 power what? 5. But they are frequently colliding with the other electrons, other positive charges, the wall of the your conductor, so that their overall displacement is what? Almost zero only, correct. If displacement zero, average displacement zero, then velocity also becomes what? Zero. Speed, they have individual speed this much, but if we talk overall speed of all people together, average speed, it becomes what? Zero. So very important point I'm saying. Let me write few words. As electrons are randomly moving, they collide frequently, okay, frequently with other electrons, positive charges and walls of what? I will write correctly, of conductor. Due to this, what's happening? Okay, electrons are randomly moving, so they are colliding frequently with what? The other electrons, okay, positive charge and walls of the conductor, so their net displacement. So let me write one word. So due to this, what happened? Correct na? Their directions changing frequently, okay. Okay, once more, let us start. What happening? Electrons are randomly moving, okay, randomly moving, so they are colliding with what? Other peoples, like electrons, positive charge and wall of the conductor. Due to this, what happened? The direction getting changed frequently. Due to this, what happening? The overall displacement remains what? Zero. They are moving and all electrons are moving and moving at what? Very high speed. But what happened? Very frequently they are colliding what? Other people, so their direction getting changed, okay. Yes, I told you this room again, and if you put one drunken man, it will colliding with the wall of the this room only, right. But if you put 10 drunken people here, okay, yes, and all of them are moving, then what they do? Obviously they will collide with what? Each other, with the walls, right. Yes, so they are moving, these all people in this closed room, they are moving and moving at very high speed, but the overall displacement of these people are zero only, because these people remains in that room only, right. They are not going anywhere else outside, right. So net displacement of these people zero, net displacement zero, which net average velocity you call this, right. Average displacement zero, so average velocity also becomes what? Zero. So now writing very important. So the average velocity of all electrons, if you take together, you take average of them, is what? Zero. So do not confuse now, very important. If they ask that what is the thermal speed of the electrons, it's not 0. Thermal speed is what? 10 power 5 meter per second. Yes, they are moving at what? Very, very high speed, right? 10 power 5 meter per second. But you talk the what is average velocity of all these electrons together when no field is applied. What is the answer? 0. Average velocity becomes 0 because average displacement is what? 0. Hope you understood this. This is happening when no field is applied, okay? So thermal speed and velocity. Right now thermal speed is there, yes, speed is there, 10 power 5 meter per second, very high. But the average speed you talk, sorry, average velocity you talk, okay, all people together, then average velocity of all these electrons becomes what? 0. Correct? Suppose you want to write like V average of all people, velocity of first guy, second guy, it's a vector quantity, okay, yes, plus third guy, you add the velocities of all people, then divide by number of the electron, this becomes always what? 0. Okay, let's write a U symbol here, so that next step I can write V symbol. Okay, U symbol. So these are the individual velocities of each. What velocities? Your thermal velocities, right, for each. Then you take average of this, is always become 0. Yes. Okay. So here you define one or two more terms. So one term is called, okay, thermal speed and velocity. I have discussed you. Thermal speed is there, but velocity, average velocity is always what? 0, because net displacement of all the electrons inside a conductor is always 0. They are moving randomly, their direction changing frequently. So overall they doesn't move. Okay, they remains in that wire itself. Okay. Now see what happens. Some other terms they talk here. So one is called relaxation time. Something called relaxation time, tau symbol, the right. Okay, so I said these electrons are moving and moving at very high speed, you see, and they are frequently colliding. Okay, so how much time they take? Average time between two collision, that's called what? Relaxation time. Okay, so how they define relaxation time? Is the time, it is the average time between what? Two successive collision of what? Electrons. How much average time they take between two collisions? That's called what? Relaxation time. And this time is what? Very, very small. If you want to write in numbers, then this come around 10 power minus 14 second. Very, very small time. So they are colliding what? Very, very frequently. So why I am telling this term? Because later when we talk a numerical part of this term will come. Okay, relaxation time is the average time taken between two successive collision of the electron. Okay, and this value is around 10 power what? Minus 14 second. Okay, one more term they use here is called mean free path. Mean free path. Okay, so all these three terms are talking when what happening? When no field is applied, no external field is applied, or no potential or no battery is connected to this wire, just wire alone, then what happening? There are large number of free electrons, they are randomly moving, correct? Their direction changing frequently. So overall the displacement of all electrons becomes 0. So net velocity or average velocity of all people together becomes what? 0. Okay, yes. Okay, relaxation time I did. Then average, what is mean free path? You can write a lambda symbol here, generally write like this symbol only. Okay, what is the mean free path? Same like this only. The average time between two collision, correct na? That's called your relaxation time. Same the average distance traveled between two collision, that's called what? Your mean free path. So same way it is average distance electron travels before what? Same two collision, okay, successive collision. That's what your mean free path, correct? Okay, three terms are there, small terms, little useful later. Okay, so relaxation time is okay. How much this? Okay, like I gave the relaxation time is around what? 10 power minus 14 second. Same way, if you want to define mathematically that how much this time? So this almost approximately this value is how much? 10 angstrom. How much this distance? 10 angstrom. Okay, angstrom is 10 power minus 10 meter. So this is actually distance, mean free path, the average distance between electrons, average distance electron travels before what successive collision. That distance is called what, your mean free path, and the time between two successive collision is called what, relaxation time. Thermal speed, yes, thermal speed is there, 10 power 5 meter per second, but average velocity of the all electrons when no field is applied is what, 0. Okay, so now what we will do, we will apply field toward this wire, means we will connect this wire to a battery like this, then what will happen we will see. Okay, so now we are seeing the second side. Okay, first what we did, we took a wire just and we applying no external field or no potential, then we seeing that how these electrons are behaving. Okay, so electrons were randomly moving, so that the net displacement and average velocity of all the electrons together in a wire becomes what, 0. Okay, now what happens, behavior of electrons or other charged particles, okay, when external field or you say potential is what, applied. So same wire that we took last time, just connect a battery with that. This is a wire, this is the area of cross section, and we connect a battery with this wire like this. We are supplying some potential here or field here. Okay, here first I want to tell you important things. This will learn in electrostatic also, the direction of field. Okay, so let me write that. I am continuing from here. Direction of what, electric field. What's the direction of electric field? Already will if you know basic from electrostatic is from positive charge to negative charge. Yes, correct only. Okay, or how you say here, because your current is flowing, so how you will say here, direction of electric field is simply direction of your positive charge or direction of your current. Okay, direction of what, of positive charge flow, or you can also simply direction of current also. Okay, whatever direction of current, that's your direction of your field in case of what, current electricity. Okay, so current is flowing like this way, that's direction of your field also. Okay, electric field. Now look here, so behavior of electrons when external field is applied. Electrons were here randomly moving. Now what we did, we applied a field here. So we have applied field means we applied a force on that. Which force? Electric force. So what happens when, look, I am writing, so when external field is applied, we have applied what, external field. Due to this what happens, electrons get experience of electric force. These electrons or charges, electrons will experience electric force, correct na? Yes, force will be exerted on that, and how much force? Q into E. Force we have learned in last electrostatic general formula, charge into force is called force, electric field, so E into E. Okay, and we put negative because electron is what, negative. So force is what, Q into E, charge into electric field, that's called electric force, right now. Electric force, what is formula? Q into what, E, this is the electric force. So here charge means what, electrons, I am putting E, that's electric field. Okay, yes. Now look here, what happens, this is electric, so electrons will experience electric force, this much force, I should write force word here. Okay, electric force. So when field is applied or battery connected, what happens, electric field is set up in the wire, so all electrons will experience a force. That force is what, electric force, how much, QE or E into E, right? Now when you are applying external force, that is external force when we apply on any body, what happens, body get what, accelerated, right? Acceleration happens. So what happens, external force applied, electrons will get accelerated. And how much acceleration? Acceleration simply force by mass, that's called acceleration, because force is also equal to what, ma, right? Mass into acceleration. So here you want to calculate acceleration. What is acceleration? Obviously force is what, this much minus E by, and mass is what, m. So this is your acceleration we are getting. So electrons get accelerated, all electrons, right? Yes. So now we have force in one particular direction, so electrons start moving in what, in one particular direction, they get aligned. Okay, almost they get what, aligned, and they start moving. Okay, so what happens, because they are getting aligned, so the collision is what, less, the number of collisions got reduced. They are not colliding now frequently because they are moving aligned in one line. Okay, remember last time what I said, that case, like these are drunken men in a room and they are randomly moving. If you move randomly, obviously what, they will collide. But you see, like army parade, so army people, they are doing parade, they move in one line, they walk in one line in proper order, right? Everybody walk with same speed in same way, right now. So they don't collide, right? So they keep moving, so they have a net displacement. Like this is army people, this is what, your drunken people, right now. Yes, so here they are randomly moving, so net displacement 0, but the army people, they move in proper order right now with same velocity, everyone in same direction, so they are not colliding. So there they have what, net displacement, so they will have what, a net velocity also, right? Same thing happening here. These electrons, now they started moving on one proper order, okay, like in one they get aligned because everybody is getting experienced a force in what, same direction of same amount, okay. So they start moving in what, in one particular direction in order. So now the number of collisions is reduced, so they will have an overall displacement and overall velocity. Okay, let's see. So when external field is applied, what happens? Electron will experience electric force, yes, this much force, Q into E, okay. So if you're getting X force, then what happens? Electron will get accelerated, yes, this is the acceleration, right? So now they will have a net velocity. So due to this, what will happen? Electrons will gain net velocity, right now, and this velocity also called what, drift velocity. So the velocity getting due to the drifting, why they calling it drift? Because electrons are drifting in one proper direction, okay. Yes, so this is also called drift velocity. So external force is applied due to this battery, so electrons started moving in one particular direction, so they are drifting in one particular direction, so they overall they have a velocity. That velocity is called what, drift velocity. So let's how to write this now. Look here, initial velocity we know, acceleration we know, and we want to find final velocity, so we can write equation of motion. First equation, you know what is first equation? V is equal to U plus what, AT, right? This is the equation, first equation, right? So you're writing what is final average velocity of all these electrons, which is also called drift velocity, okay? So let's write here heading as drift velocity. Correct, na? Yes, they are drifting, yes, slowly they are drifting. So what is the hope you remember, understand the meaning of drift word, like you have seen some movie also, like Tokyo Drift, right now, Fast and Furious series. Drift means what? You're moving slowly in one proper order, right now. Yes, all cars are drifting on a road slowly, right now. So drift means what? Slow. That's okay, drifting, slowing. So they gain velocity, but that velocity is what? Very small actually. So we call that what? Drift velocity. So how much that? We're calculating from this formula. V, what is this? Initial average velocity of all people together. When no field is applied, it was 0. So this term is what? 0. What is acceleration? Yes, this is acceleration here, right? So I'm writing here, okay, plus E by m, okay, this is your acceleration, into what? Time. Time is called what here? Tau, relaxation time. I told you definition, the time taken between two successive collisions, that's called relaxation time. So that time is what here. So now I wrote here, you can write the average, okay. So final average velocity, or you called, okay, we write actually D symbol here, so we call drift velocity, okay. So what is the velocity once more? Drift velocity is equal to what? Minus E by m into what? Tau. This is what your drift velocity of the electrons. Meanings of all symbol, you know. Charge, electric field, let me write charge of each electron, right, which you know already, 1.6 into 10 power minus 19 is what? Your electric field, how much electric field you are supplying, correct. Okay, m is the mass of each electron, this also you know, 9.1 into 10 power minus 31, and tau is what? Your relaxation time. Relaxation time. So the average time taken between what? Two collisions. This is what your drift velocity. First numerically important thing we can see is what? This one, okay, drift velocity. So what is drift velocity? when external field is applied, all the electrons experience a force in what? One particular direction. How much force? Q into E, charge into electric field, right? Yes. So they get accelerated in what? One direction. So what is acceleration? Force by mass. Force by what? Mass of the electron. So they gain a velocity. That velocity is called what? Drift velocity. So numerically, if you see, the drift velocity is what? The order of this drift velocity is what? Around 10 power minus 4 meter per second. Watch it carefully. It's very small speed, right now. Very low. How much? 10 power minus 4 meter per second. Yes, it's very small. Yes, correct only. That's why they're calling it drift velocity. Drift means slowly drifting. Okay. Yes. So remember, when no field is applying, do not confuse. Like if they ask that electron is moving, they are randomly moving, what's the thermal speed of these electrons? It's very high, 10 power 5 meter per second. But they ask you drift velocity of these electrons. Overall, what is the total net velocity? Okay, what is the answer? 10 power minus 4 meter per second. It's very small, keep in mind. Okay. So what we have done, we have found the drift velocity, which is important for us. Okay. Yes. Now we will continue from here. I will try to calculate that what is the net current. Still we not found the answer of this, that what is the net current now that flows in this wire. Okay, what is the net current flowing through this wire? We want to calculate. Okay, so here we need to write some physical dimension. A is the area of cross section, L is the length of this wire. Okay, so let's find current. I'm writing first symbol here. What symbol? Look here. L is what? Length of wire, suppose, and A is what? Area of cross section, right? And let me write few more terms. Small n, this term already we learned in last chapter. So semiconductor is a number density, right? Number, how many charges or how many electrons or holes per unit volume. That's we represent by what? N symbol. So small n is what? Number of electrons here per meter cube, means density of the electron n. Okay. Yes. Okay. Let's see. Now what we do? We start from here. Okay. One at the starting I told you the current general equation. Current is what? Rate of flow of charge, Q by T, right? And one equation what here? These two will use together and find the current relation. Okay. So first already we have learned current is nothing but Q by what? T. Total charge by time. That's what your current is. So one equation we using this and one we using here. Vd is equal to what? E by m into tau, right? So watch carefully. We need to calculate what is total charge first. What is total charge inside this wire? Okay. We have wire of length L, area of cross section A, right? And this is the density of the electrons in that wire. We want to calculate what is total charge. So let's calculate total charge. Q. Q means what? Your total charge in wire. This you want to calculate. So how to calculate? Look here, very simple. What is N? N is the number of the electrons per meter cube. So what is total number of the electrons first? N. Watch carefully. N, right? There's a number of the electrons per meter cube. So total you want to find, you have to multiply what? Volume here, right? Because it's a density. So volume is what? Area into length. Area into length. Okay. Yes. Now this is the density, number of the electrons per meter cube. So I'm finding what is total number of the electrons, and density into what? Volume. Okay. This is what? Total number of the electrons, right? And what is charge of each electron? E. So you multiply what? E here. Now this becomes total charge inside that wire. Hope you understood. Once more. N is the density, number of the electrons per meter cube. So you want to find total number of the electrons, you multiplying with what? Volume. Area into length, area of cross section into length, that's called what? Your volume simply. Okay. Into charge of each electron is what? E. So this becomes total charge. Okay. So let's write that equation. How you say? Current is equal to what? E N A L by what? T. Correct? Time. Now look here, watch carefully. Length by time. One electron start from this point, it want to come at that point. Total distance travel is, displacement is what? L. Okay, time taken is what? T. So that distance by time, that becomes what? Your velocity. Which velocity? Drift velocity. Distance means length of the wire. You want to go from this end to that end. So distance travel is what? Simply length of the wire, correct? Properly displacement, what we should say. So this by that becomes what? Your drift velocity. So current is what? We arrange this like N, E, A, and this we call as what? VD. So here I am nothing but I am writing L, length of the wire, by time. This I am calling what? Drift velocity, correct? So this is what second important thing we got, the current formula in terms of what? Drift velocity. And this already I told you in last chapter also, semiconductor, right? Now this formula came there, right? Here we have only electrons in this chapter, so only just one way to write. Last chapter semiconductor, we can have electron and hole both in semiconductor. So current will be due to two things, current due to holes plus current due to what? Electrons. So generally what will different, this number is different and drift velocity is different, right? Now yes. So watch carefully, current in a wire, right? This is important. Second thing, okay, one thing we have learned drift velocity already here, because small theory question they asked you about this, I will discuss later. So this is a current. How much current in a wire? NEAVD. Density of this electrons per meter cube, charge of each electron, area of cross section, and what? Drift velocity of the electrons, right? Okay, second important thing is what? In front of you, okay, current in a wire. Okay, so from here we will define few more things, okay, then I will do some questions on these, okay. So what I'm defining is this, some definition. So something we want to calculate from this equation, you want to see the what is Ohm's law you want to calculate, okay, and some definitions will come like what is current, density, mobility, and these things. So let's see. First I want to calculate Ohm's law from here, okay. So this is also called okay, let me write just Ohm's law itself, okay. Yes, current and potential relation, that's where Ohm's law. So how that coming from here, let's see. What I do, I pick this equation again. So current is equal to what? NEAVD, and in this VD let's put the value from here, okay. So what I'm doing, I'm putting VD value, drift velocity value, which is what? Okay, I'm just putting numerical part only, not that sign, just okay, and tau, this much. Let's put it here. You see current becomes what? NEA, this becomes EE by M into what? Tau, correct? Now what I do now, again I replace what? Electric field, because generally what we know potential of the battery, okay. So we don't know electric field, we can calculate, but what we know generally is potential. So let's write this formula in terms of potential. So already many times we have discussed, last chapter also I told you potential and field relations, right? So electric field is nothing but when potential by what? Length of the wire. Yes, yes. In correct formula is actually is a potential gradient is called what? Electric field, but we don't need right now here, so I'm not using general way, okay. So electric field is what? Potential by length. Let's replace it here. So look here, current is equal to what? N EV got square, there is one E here, area, this is M, and tau is there. Electric field is what? Potential by length, so V by what? L, correct? Okay, so now what I do, I just rearranging this formula only. How? V I am taking down here, so I by V, okay, done, is equal to, now we got N E square tau, I put here, mass area by what? Length, correct? Yes, area by length, okay. Now this is, reverse this, okay, V by I is equal to, it's called M N E square tau, length by area. So hope you can recognize something here, right? Yes. So V by I, you call it what? Resistance, right? Yes. So this is what your Ohm's law's microscopic form. Look here, in this part is what? Constant part. Mass of the electrons constant, density in one particular conductor is constant, charge constant, relaxation time also constant. What can vary is what? Length of that wire and area of cross on this part is a constant. So first this V by I, this is called resistance, right? Yes. So this part, resistance is equal to M and E square tau, length by area. So this is a resistance formula, and this is also constant. So this is called what? Resistivity. What is called? So resistivity Vt. We write what? Rho symbol for this. So rho is nothing but what? Watch carefully. M n a square tau. This is called resistivity, which is constant. Correct, na? Yes. So resistance is what? This much. Resistance, or you can also write V by I. This is called your Ohm's law only, right? And this part is the constant. That's called what? Your resistivity. So resistance also equal to, you know, that you can also write rho into what? L by A. This is a general formula you have seen many times everywhere, right? So this is your Ohm's law. Yes. So watch carefully how you will getting all this from here itself, current, right? In current formula, I am just putting what? Your drift velocity, and I am replacing two things here, electric field in terms of potential, then potential by current, that's called your resistance. So resistance is what? This some constant into what? Length by what? Area. So this constant is called simply resistivity, right? And this is what? Your resistance, okay? Yes. Okay. So there are few more terms, I will not go there. Before that, okay, let me discuss all the terms here, then I can do problem on this. So I will discuss small terms here, then how this resistivity depends on temperature, that I will discuss. This much theory I will do. After that I will do problems, okay.